Croeso cynnes I chi gyd I Bangor. A very, very warm welcome to you all to Bangor University and to OR66. It's a real pleasure to welcome you all here. My name's Edmund Burke. I'm Vice-Chancellor of Bangor University and a past President of the OR Society. And it's not only a significant event for the Operational Research Society, but it's a really significant event for us here at Bangor University. It's a tremendous honour and it's a privilege to be hosting this university. This conference at this university. As president, serving this community for 3 years through the COVID pandemic, it was really challenging for the society as the pandemic hit. Serving was a real privilege, and I was delighted to be able to do it. Now, it's been over 30 years since Bangor University hosted the OR Society Conference back at OR32. And much has changed since then for the university and for the society. But one thing that's constant is the natural beauty of this region, here between the mountains and the sea. And please do take the opportunity to make the most of it. It's a beautiful, beautiful region and a very, very warm and welcoming community. Now, this year's conference is particularly special as we celebrate two major milestones: the conclusion of the OR Society's 75th anniversary and Bangor University's 140th anniversary. And the story of the founding of this university really is inspirational. In the modern parlance, it would be called a crowdfunding scheme. In Victorian times, it was called a penny fund. And the local people, the slate miners, the agricultural workers, they understood the transformative power of education. They understood what a university like this could do for their children, their grandchildren and future generations. And here we are, exactly 140 years later, with their legacy at this fantastic university. So for over a century, Bangor has been a beacon of research and education in this region. And it feels fitting to celebrate that rich legacy and the bright future of operational research here at this institution. I'm especially delighted by the diversity and strength of participation at this year's event. We've had over 280 delegates and more than 200 accepted abstracts. It's really fantastic, and I'm very much looking forward to the conference and looking forward to engaging with you all. It's fantastic to see so many key representatives here from NHS Wales, NHS England, UK Government, Welsh Government, UKRI, EPSRC, the Office for National Statistics, DEFRA, DWP, the National Audit Office, HMRC, and so many other organisations. Really fantastic to see you all here. Your presence is a testament to the vibrant and vital role that operational research plays in addressing the societal challenges of today. As mentioned, Bangor University has a rich history based on the collective effort that built this institution. That same spirit continues to guide us as we focus not only on academic excellence, but also on making a tangible impact on society. Our dedication to the third sector and pro bono work is strongly reflected in this year's conference themes. We will tackle critical global challenges, including social unrest, gender equality and sustainability, in alignment with the FA of Wales Sustainability Strategy 2030 and the United Nations Football for the Girls campaign. Operational research is, at its heart, about solving real-world problems. And this conference will address a wide range of pressing issues, from sustainable agriculture and public health to driving innovations in the private sector. Our session on delivering more effective knowledge exchange between academia and industry is particularly relevant for this university, as it speaks directly to Bangor's long-standing role as a key driver of the North Wales economy. One area where Bangor has made historical contributions in aerospace is the pioneering work of Professor George Hartley Bryan, who in 1911 developed the mathematical equations that still govern aircraft motion. It continues to influence aviation today. Our collaborations with companies like Airbus demonstrate Bangor's ongoing commitment to innovation. And we're also really looking forward to hearing from Dr. Jeroen Mulder of Air France KLM, who's going to share insights into the operational research challenges within the aviation sector. And I've known Jeroen for, we were trying to work out whether it was 2001 or 2002, but we published a paper together in 2003, so it was some time before then. And it's a real pleasure to welcome you to Bangor and to the Operational Research Society Conference. And as we look to the future, healthcare is another area of growing importance for Bangor University. We have a brand new medical school starting this month. Our first students start. We have pharmacy starting next year. We are strongly committed to healthcare in this region, to Welsh medium teaching in healthcare, and to the ongoing well-being of the residents of this region. So it's really pleasing to see that this conference also reflects a commitment to healthcare, with over 20 submissions and a plenary talk from Professor Sanja Petrovic, who will address how OR can improve healthcare outcomes. We're really excited to continue collaborating in this critical field. So, in closing, I'd like to extend my very warm thanks to the Operational Research Society for bringing OR66 to Bangor. I'd like to thank all the organisers. I know a lot of people have put a lot of effort into it, and it might be a little bit premature to issue thanks at the beginning of the conference. We should perhaps wait until the end. And I don't want to, if I try and list a whole lot of people, I risk forgetting someone. But I do want to pick out Mossab and Caitlin, who've worked really hard. Thank you. So that's it for me. Have a great conference. I'm delighted to see you all here. I repeat my very warm welcome to Bangor University. Diolch yn fawr I chi gyd am mwynhau y wythnos. Thank you all and enjoy the week. Diolch. Shall I? Is that the one I want to use?
Good morning, everyone. It's my pleasure to introduce our first plenary speaker, Dr. Jeroen Mulder. Dr. Mulder is a technology innovation project manager at Air France KLM. In his role, he drives innovation through cutting-edge technologies such as quantum technologies and generative AI. With a strong background in mathematics and a PhD in algebraic methodology, he brings over 25 years of industrial experience as an operational research analyst and data scientist. He has developed optimization, simulation, and statistical models for key business areas such as operation business center, operation hub centers, and engineering, maintenance, and revenue management. He was also part of a very large team at Air France KLM that develop optimization models and forecasting for the joint revenue management of Air France and KLM when they join together. In his speech today, he will walk us through operational research challenges at Air France KLM. Please join me in welcoming Dr. Jeroen Mulder to the stage.
Yes, just checking whether you can hear me, but I think I can hear me, so this is working. So thank you very much for this very nice introduction. I think I'm blushing, but thanks. I would also like to thank the organization, Operational Research Society, for inviting me to do this plenary talk. I'm quite honored about that. I can skip my introduction, so that saves me a bit of time. So I will first say some words about Air France KLM. So by the way, Jeroen Mulder, that's me. Air France KLM I'm working for. And Air France KLM is a large European network carrier. We have two hubs, one in Paris, that's Charles de Gaulle, one in Amsterdam, that's Schiphol, and we have three key areas of expertise. I will come back to that.
I can't hear you, I've just got to work out how to turn the mic off.
This mic is off, but this mic should be working. Is it better?
Is that better? Yeah.
Okay. Should I restart? No. Thanks, very kind. So I was saying that, let's say, we have the central hubs in Paris and in Schiphol. And I put here, let's say, the mission statement that we had some years ago. So that's also our focus. What we try to do as an airline is to be the most customer-centric, efficient European network carrier. And what we aim to do is to have the most attractive network, including all stakeholders, and find an optimal match between commercial wishes and operational capabilities. And some of these words are highlighted, and the reason for that is that, let's say, it's the topic of my presentation. It will come back in the further slides. I'm okay? Yep, perfect. First, some words about the key areas I discussed about. So I will try to do this, well, not in all the details, but basically we transport passengers. So last year we transported 94 million passengers to 320 destinations. We had 100 countries where, let's say, the people were going to. Next to passengers, we also transport cargo. So we have 6 full freighters, and we carry also the cargo in the bellies of our aircraft. So that's about 80%. And the volumes in this case were 875 kilotons of cargo last year. What most people sometimes don't know is that we also have, let's say, this third key area of expertise, and that's engineering and maintenance. So we also maintain aircraft, our own aircraft, but also aircraft of other airlines. So we maintained 3,000 aircraft last year for 200 customer airlines, and that makes us the second largest global player in the world if you talk about MRO, so maintenance, repair, and overhaul. Just good to mention. Today, I would like to talk about the challenges on the operational research side. And therefore, I think it's good to have a kind of overview of, let's say, our planning process. This diagram is coming from the book. It's on the bottom, The Global Airline Industry by Peter Belobaba, Amadeo Odoni, and Cynthia Barnard. And basically, it sketched, let's say, the planning that we do, starting 4 or 5 years before, until, let's say, the day of operations. We start with fleet planning, so which aircraft do you want to buy, how many, which types. Then we go to route planning, so which markets do you want to serve, which markets do you want to, let's say, draw back from. Then, if, let's say, that's clear, you look at your schedule development. So you determine on those routes which flights should be scheduled, the frequency. You make it even more concrete into timetables. You assign aircraft types to those flights. So if you expect a lot of demand, large aircraft, if it's less, smaller aircraft. And in the end, you assemble the aircraft rotations. Then you have those two branches. The first one is still focusing more on the, let's say, the demand that you have in mind. So it's about, let's say, reaching out to your customers. So it's about pricing, revenue management, sales and distribution. And the other part is more the operational part. So it's about crew scheduling, it's about airport resource management, and it's about the operations control. So what you do on the day of operations itself. There are many challenges. So I reached out to colleagues working in all these fields to ask them, okay, what challenges do you encounter at this moment? And challenges can be things that they cannot mention at this moment. Yep. So it could be things that you cannot mention at this moment. I'm still hearable. That you cannot mention at this moment because, let's say, it takes too much time to do, let's say, the computations. can also be due to the fact that it's very difficult to convince your business to go along with you. And also, let's say, sometimes the mathematical method that you are using is not that clear. You also have to work on that part. Basically, the challenges that they mentioned to me, and these are the topics for today, is demand modeling, it's dynamic pricing, digital marketing, hub and network optimization, predictive maintenance, and disruption management. There's a seventh one, and that's giving this presentation in the time given, so I will do my best for that. We go to the first challenge, and that's demand modeling. So basically, that's what you do. And when you talk about, let's say, the fleet planning, the route planning. And just to give you an idea, so when we work on these, let's say, the fleet planning, the route planning, we need to have a good estimation of the demand that we expect. So to give you an example, suppose you would like to estimate the demand from passengers going from Milan to New York. How does it work? Well, Milan has 3 airports nearby, New York has 3 airports nearby, so we already have a lot of different combinations there. First, you try to estimate the demand on this level, and then you look at all possible combinations. So there are a lot of direct flights that you can take, but you can also transfer, for example, in New York, or you can transfer in the States. So giving you a lot of different options, and the overall demand that you estimated, you need to allocate it to all of these different options. Basically, that's what you do with demand modeling. So the first part is demand generation, overall demand for your market. The second one is demand allocation, so for all of these different options. The first thing, so demand generation, what you can do is you can use, let's say, the so-called gravity models. And gravity models are based on, let's say, Newton's law of gravity. So basically you have this formula that you see there on the right, and you have all kinds of features where you try to include them. And these features can be, for example, the population size, the GDP, the frequency of the flights. It's called Newton's, it's called the gravity model, based on Newton's law. Basically because it resembles things. So some of the features are attractive, some of the features are repulsive, and based on that, let's say, you try to estimate your coefficients. And the way you can do it, well, you just take the logarithm of this expression, you get kind of linear expression, then you use linear regression, and in that way you try to estimate those values. Yep. In this case, you have you estimated the overall demand for this market, and now you want to look at the specific options, the itineraries that you have for, say, this O&D market, and you need to estimate the kind of score of each of those itineraries. The first way you can do it is what they call the quality of service index, and the other method, and I will also have some slides on that part, is that they're using discrete choice models. Basically what you do is you try to estimate the score. When you have the score, then you also look at the scores of the other itineraries, you sum it up, and this gives you a kind of percentage. And with the QSI, that's directly representing your market share. And with the discrete choice models, you do it a bit more, let's say, advanced, using statistical methods. This is what we do with QSI. So QSI, in fact, is a very simple expression. So you assume that the score that you do for your itinerary is just a linear expression based on some of the features. And the features, so you see the expression over here, are things like flight frequency, type of flight, aircraft type, onboard services, and so on. This linear expression, you have the weights, and then the challenge is to have the right weights. The nice thing of this expression is that it's quite a simple expression. You can discuss with your business about these weights. So there's really a business involved. It can, say, be explained to your business, but it can also be explained by your business. And that makes it a quite strong model. So simple to calculate. The market share, as I just mentioned, is then proportional to the score that you calculated. And it's very simple, intuitive for the business user. That's really helpful. And it has limitations, and these are also mentioned over here. So the first thing is that you assume that the attributes, the features, are independent of each other. So you have independent weighting of your attributes, and it's quite restrictive because you don't capture, let's say, the interaction between some of those attributes. So the other thing, for example, is also it's not able to detect sweet spots because you assume a linear expression. Sweet spot, for example, connection time. So connection time, the optimal value is in a certain range. So if it's below or if it's above the range, the connection is not that interesting for your passenger. So if you use a linear expression, that does not work. The other way you can do it is more a statistical approach, where you use the maximum likelihood to, let's say, compute the probability that a passenger would, let's say, go for a certain destination, would choose a certain itinerary. You base it on a utility function, so that's a part of the discrete choice modeling that you need to do, and this utility function is then expressing, based on the different features, again, what we saw also in the QSI, say the value that you want to optimize in some way. So this utility depends on the attributes of your itineraries, so the different choices that you have, but it's also depending on the characteristics of your passenger. So that's what we call segmentation. And basically the utility you try to estimate in some way is consisting of, it's composed of a deterministic part, so that's the V that you see over here, and there's also a random part in there that you also have to incorporate in some way. And then based on the theory for discrete choice modeling, you can use the formula over there. So you take the deterministic part, you have, let's say, all the attributes there that you can estimate or that you can compute, and based on that you can estimate the market share using this kind of softmax functionality. There are some assumptions that you should make on the error distribution. So if you assume that, let's say, it's IID, and in that case, let's say you come to the very simple formulation of a discrete choice model, and that's the multinomial logic model. And basically that's what we are using or trying to use also inside our company. So the strength, sorry, too soon. So the strength of this way is, let's say, it's very advanced. So you can really model a range of choices, and you can really look at the characteristics of your passengers to really see what kind of choice you would make and to do the computations. So that's really the strong point. It's, let's say, it's looking at your individuals, so it's trying to, let's say, have more insight in what your individual is doing, based on the preferences, but also based on the attractiveness of your itineraries. So that's, let's say, what we saw also with the QSI, but here's also incorporating the preferences of your passengers. However, there are limitations, so it requires large amounts of data, large amounts of computations, they are quite intensive, so that makes it quite difficult to, let's say, really tune the model in a good way. And also, I think that's more, let's say, the statistical part, there are also some assumptions about these error distributions, and they do not always hold. So that means that your model sometimes is not doing what you expect it will be doing. These, let's say, are two ways, let's say, of trying to estimate this market share. If you look at QSI versus MNL, so at KL, I think also at France, we started with QSI already many years ago. And I think the plain QSI, where you have this kind of linear expression, so that's a very simple one, that's considered as a white box for our users. So it can be explained by the users to the user. It's really, clear for them why some of those ways have certain values. If you look at the MNL, so the discrete choice modeling, it's training, let's say, on market share data, historical market share data, and at some moment you have some weights. That's difficult for let's say, the business. So they consider it as a black box. What are we doing? So I already mentioned that we start with QSI. I also showed that, let's say, there are some disadvantages of QSI. So what we are doing is a kind of in between. So I said, okay, our QSI is a kind of gray box. So we have more than 50 years of business knowledge put in this linear QSI. And at some moment we saw, okay, the linear formulation is not working. So we made some adjustments, and in fact, in some cases we saw it's not working there. So we made kind of a combination of categorical and linear expression. So that means that it's gray, because, it's still business knowledge, but sometimes you don't know where the business knowledge was coming from, because it's already quite long ago. Yes, so that's, let's say, the part about the QSI that we are currently using. We know from the theory that let's say, the discrete choice models, or the MNL, is a better way of doing things. So what we tried ourselves is we tried to do some experiments using the QSI, and so using the MNL. And what we saw is that our first experiences here, on a very high level, made sense. So they were, let's say, not that different from our own QSI model. So that seems to be good news, but if you think about that, so the scales that we tested with, just to see, okay, is this MNL working, they were created with QSI. And if you have, let's say, scales created with QSI and you try to train an MNL model, probably you'll get something like a QSI model. So the challenge that we have here is to see, okay, how can we really make this step to really say, be M&L based. Let's say the challenge is how do you onboard your business? They've been using the QSI for many, many years. So it's really a kind of mind shift that they need to do. How can you ensure that M&L is not just another QSI? So that's also one of the challenges. And how can you also model this one? So the interaction between demand generation and demand allocation. So some words on that part. So what we see is that sometimes when you open new itineraries, there's more demand for the whole market. So basically what you try to do is to try to balance the total market over the different itineraries. Sometimes when you open new itineraries, you see that the demand is also increasing. So there's interaction between those two steps, and that's not done yet. So that's also something we are looking into. First challenge, I'll go to the next challenge. That's dynamic pricing. What you try to do with dynamic pricing is to make the best offer towards your customer. So at some moment your customer would like to go somewhere, you would like to buy a ticket, and basically you would like to know everything about your customer to make the best offer to this customer. What we do, that's what we saw in this planning process, we do revenue management. We do pricing revenue management, that's based on forecast. That's based on, let's say, the things that we have seen, let's say, the years before. And let's say it's based on the bookings that are already made. It's not based on the customer actually trying to make a booking. So you don't see the actual customer yet when you do revenue management. And dynamic pricing is an approach to really, let's say, offer the best price towards your customer in real time. And what we always say is it's selling the right seat to the right customer at the right price and the right time. So why do you want to do this? Well, I think it's good for our company because we are trying to maximize our revenue. It's also better for our inventory management. So sometimes you see that you are lacking behind. So you really can, let's say, try to correct that by maybe lowering the price a bit. And also I think it's improved customer segmentation. So it's also offering a better service towards your customer because you know more details about this customer so you can make, let's say, a better offer to this customer. Why do we do it now? Let's say we already tried to do it since a couple of years. That's based, let's say, the main drivers are technological advancements, and also, let's say, the data quantity and the quality is really improved. I will try to explain a bit, let's say, this link that you have between revenue management and dynamic pricing. So it's the dual structure of the price optimization. And based on what I just told you before, that revenue management is based on, let's say, the forecast demand, bookings made so far, and based on that you try to compute what we call bid prices. And bid price is the minimum acceptable price you want to sell your ticket on the flight for. It's based on forecast demand, also, let's say, remaining capacity, and dynamic pricing really looks at this individual customer and then tries to really optimize the revenue on the spot. So what you do on the one hand is you try to look at the opportunity cost, so the bid prices coming from your revenue management system, and you try to make a price or to set a price based on the customer that you are currently seeing at that moment. What would you like to know from your customer? Well, basically, if you offer a price, you would like to know if he's willing to go for this price. So you should try to estimate the so-called willingness to pay of your passenger. And that's the maximum amount the customer is willing to pay for the ticket. This willingness to pay is something you try to model, you try to estimate, and it's based on, again, the segmentation, so what kind of passenger it is, and also the choice that you are offering. And just to give you an impression, so if you have a customer booking far from departure, say half year before departure, he's not willing to pay the same price as a customer, let's say, just 1 day before departure. So that's, I think, one of the characteristics of the passenger, making a difference. Also, if you have a customer, let's say, that's having a direct itinerary, he's willing to pay more than, let's say, for an indirect itinerary. So these kind of characteristics, let's say, are making a difference. So what we do, so we have this willingness to pay, and in some way you need to translate it to probabilities. So what we try to do, and that's what you see in this formula, we try to measure, or we try to estimate the purchase probability given the price that we are offering. And then based on that, we set a price, we correct for the tax and, let's say, this bid price, opportunity cost, and based on that you can compute the expected revenue. And the idea is that you play a bit with the prices, and then based on that try to find optimal value so you have the most expected revenue. That's basically what you try to do. How do you compute this probability? Again, that is something you do with discrete choice modeling. It's quite similar to what we saw before. But maybe just first to give you an impression how it works, because I think the example is, let's say, telling you the most. Suppose you have, let's say, 2 customers, and they both want to go from Paris to Miami. Your first customer is, let's say, planning to stay there for 7 days, so he's on holidays, or we assume he's on holidays, so it's a leisure passenger. And the other one is only going for 4 days, so we are considering as a business passenger. They go to our website, let's say they see some options, they go to any website, whatever, and they see these 4 options. And for the moment we assume they see the same 4 options, also with the same prices. If you do it clever, probably the prices would already be different, but assume they see the same options. What you see is that this last option is the fastest, but also the most expensive. And what you see is that this first option is the longest, the slowest, but also the cheapest one. So probably what you expect is that the customer 1, let's say the leisure passenger, would go for this top choice, and let's say the business passenger would go for the last one. And now this is not working. Yep. So potential choice of customer 2 is the, let's say, the fastest and the more expensive one, and this is what you expect for your customer 1. What I said before, so we have this willingness to pay. So we try to understand, let's say, how much the customer is willing to pay for the ticket. In some way we try to convert it to a probability. So what you saw with discrete choice models, you need some kind of utility function to do the computations. So what do we do for this utility function? Well, basically we take the willingness to pay, we divide it by the price, and if the utility is greater than 1, let's say the passenger is willing to pay more than the price, so probably you will go for the ticket. If it's less than 1, probably not. So basically that's the utility function that we try to use for our discrete choice models. So how does it go? So here again an example. So we do the computations. Don't give all the formulas because that's too detailed, but assume that you compute the utility values. You see the first one is 1.1. You can then also compute the purchase probability and also the expected revenue. There we made a simplification, so the taxes and the opportunity cost are just assumed to be 0, because then it's easy to explain this example. And basically what you will see is that your customer 1 will likely choose this first itinerary. Why? Well, if you look at our offer, it's 1,395 euros. It's too expensive. So maybe you could lower the price and then see what happens. So maybe if you lower the price to 1,320 euros, you do the computations again. Then you see that the utility function is now 1.2, so it's the largest one. You will see that the purchase probability is now, let's say, the largest one. So probably this customer would now go for this option. The other customer goes the same. So if you do the computations, you see the utility function that you have for this customer too. So the business traveler is 1.6, so that's really the highest. And maybe, let's say, the offer is too good, let's say, much better than the competition. So maybe you should higher the price and see, let's say, if he's still interested in buying the ticket. So we do the same game again. So we try to, let's say, raise the price. We set it to 1,450 euros. We do the computations again, like this, and the customer is still going for this option. So in this way, you can play with the prices that you set. You try to look at the expected revenue, and you try to optimize that. And optimize is meaning as much as possible for our company. There are challenges. So what are the challenges? The first challenge is the huge volumes. And I will give you an impression of that. So if you look at our revenue management system, each day, in 1 year ahead, because if you book a ticket, you can do it, let's say, 1 year before. So for each of those days, we manage 100,000 flows. So it means that you have 365 times this 100,000 flows. If you look at the length of stay of your passenger, so either, let's say, make it in a business traveler or a leisure traveler, it can vary from 1 to 15. We have 3 classes, so economy, premium comfort, business class. On average, a flight can connect to 15 other flights, so you have, let's say, 15 connections on average. If you try to account for your competition, 3 competitors, so if you do the math, you see that you have about 74 billion different options that in some way you need to manage to be prepared for. So what's the other challenge? Well, first of all, large number, so how do you do this in a technical way? The other one is that for all those options, you don't expect that many passengers, because, well, 74 billion passengers is quite a lot. So you have very small numbers for each of those options. And that also makes it a challenge. We need to measure the effectiveness of your modeling. Next one is digital marketing. So 2 challenges I had. This one is the digital marketing. Basically, what we were talking about was trying to, well, sell the tickets to our customers. We had some how do you call it? We had some targets in mind to reach. So let's say when we looked at fleet planning and the route planning, we had in mind some, let's say, demand for these markets. Sometimes you see that you are lacking behind. So if you are lacking behind, you need to act. So what you can do is you can do, well, marketing. You can try to reach out to those customers and try to promote certain destinations and certain flights. So digital marketing is in fact about, let's say, reaching out to the right person, at the right place with the right message. So that's the advertisement that you're doing for the right price. And the right price is what we pay, because if you do advertisement on different channels, we need to pay as a company ourselves. So it's not the price paid by the customer, it's what we need to pay for this advertisement. You have questions, so how much budget should you spend on digital marketing? That depends a bit on, say, also the expected revenue that you could gain. You can then also look, okay, what are, let's say, the different destinations that you would like to promote? So if you have a given budget, some destinations maybe are lacking behind, which destinations do you push for? It relates to what we saw, let's say, in the demand modeling, also what we do with the dynamic pricing part. And also which customers do you want to target at? So these are, let's say, things that you need to account for. The most important is that, let's say, this challenge is not about the choices or the discrete choice model, but it's about, let's say, the way you try to reach out to your customers. So you can try to push, say, some ads to your customers, but you are not sure that they will really go for the ticket. So there you need to do something. So we have many channels that we use for our marketing. Things like Google search, meta search, we can do emailing, our homepage. So there are a lot of ways to reach out to your customers. And the challenge there is, so how do you track and collect all this information? Because if you want to know, say, how effective you are, you need to measure things. So basically you would try to know, you would like to know how these channels are used and also how effective they are. Say there are some mathematical ways to do this. So what we are currently doing is called multi-touch attribution. That's, let's say, the current approach. And it's a very simplified example, what you see over here, but it's, I think, trying to explain a bit how it works. You have 2 customers. The first customer gets an email from Air France KLM. He goes to our website. On the website he sees a Facebook banner. He also clicks on the search ad. And let's say for these type of customers, you see that on the average the order value is 1,200 euros. You have also another, let's say, option. So the customer receives the email. He goes directly to the website. He sees the Facebook banner, and that's it. He just, let's say, orders a ticket or not. But on the average order value is then 1,050 euros. So what you then see is that there's a difference of 150 euros, and what you then say is that this 150 euros is attributed to the fact that you had the search ad. So that's basically what we try to do with the multi-touch attribution. Sounds simple, it's very simplified, because in fact we have, let's say, many channels. So you have really you have thousands of different conversion paths that you need to account for. And some of those have more than 12 touch points, so that makes it very complicated. And it means that you need to have a kind of data-driven model to really make sense of these numbers. The multi-touch attribution is something that we are using at this moment. What I said is that you try to have as much information as possible about your customer. So you can know a lot about your customer, but at this moment there are all kinds of new laws, legislation that say that some information you cannot have or should not keep. So that makes the thing a bit more difficult than before. So basically the multi-touch attribution is something that we cannot do anymore because it's not sensitive enough anymore because of this, these new rules. So we try to go back to an already existing method, and that method is called the marketing mix modeling. And basically what you try to do is to try to use statistical methods to detect correlations between all kinds of effects. So in this example, so in the first red bar, you see the social spend on social media. It's increasing, decreasing. You see similar behavior if you look at the total sales. So in that way, it's correlated, and you try to then make a difference in the total sales, where you say, okay, this is my baseline sales, and this is the sales attribute to the social channels. In the same way, you can look at the second example. So there was no social spam at all. For example, what happened during the COVID period. Based on that, you can then say have the same kind of analysis, and you can try to detect all these kind of correlations. Again, it's about challenges. So the first challenge, again, because of the huge numbers. So we saw these thousands of different conversion paths. How do you measure your performance? So you need a good data-driven model. That's really a challenge. The next challenge is what we call the cookieless era. So you are not allowed to track all the information about your customers anymore. So that's the challenge where we go now back from the multi-touch attribution to the marketing mix model. And the last one is the commercial integration. So what you saw is that this is really related to what we do with the demand modeling. It's also what we do with dynamic pricing. So it's also about, let's say, these discrete choice models. So in some way you need to be linked to also, let's say, what the other teams are doing, the other stages in your planning process. That makes it this difficult thing because you need to connect to different stakeholders, you need to align, and you also need to have kind of consistent way of, let's say, offering those kind of choices. And that's, in a big company as Air France KLM, quite a challenge. Yep. I'm still on track, so that's perfect. I can take a breath. So the next one, that's about the network and hub optimization. I will try to explain shortly here the challenge. So I'm not sure whether everyone knows it, but you can, let's say, have different models for your network. So the first one is the point-to-point network. And that one makes sense if you have, let's say, enough local traffic, because then you can just fill your aircraft with these local passengers. When you have very small flows, it's more difficult. So there what you try to do is to fill your aircraft with different flows, and then you need to have kind of hub where you transfer your passengers. So stations are connected directly. There you see that stations are connected via hub. There you have a mix of this local and connected traffic, and there you have sufficient local traffic. The nice thing, or let's say the challenge over there, is that you have large aircraft. So let's say on average you have lower cost. So I think that's, let's say, a benefit of using this model. The other thing is that your passengers need to make a transfer. So that makes the product a bit less interesting for them. So you can only ask lower prices. So on the one hand you have, let's say, a lower cost because you have large aircraft. You have lower prices. So there's a challenge to see, okay, what is the optimum in there. Maybe just to explain a bit how it works. So if you see the pictures, I think for most airports, you have these kind of banks or waves. But basically, if you have a hub, let's say you have your aircraft, your flights coming in, they wait a moment, let's say passengers transfer, and then they go out again. There's a difference between the network that you try to support. So first you have your long-haul flights coming in, let's say the intercontinental flights, the eco flights. Then you have medium-haul flights coming in, so let's say from Europe. They go out again, because they are smaller aircraft, so they have, let's say, a shorter turnaround time. And then you have your long-haul flights going out again. Let's say, based on this structure, you can then also see, okay, what is the minimum connection time for each of those transfers. So sometimes you have people transferring from medium-haul to medium-haul, or from long-haul to long-haul, or from long-haul to medium-haul. So you have different characteristics there that you need to take care of. This is one wave. We have both at Schiphol and Charles de Gaulle, we have 7 waves. So you get this kind of picture. And this is really a challenge for our operations, because you have those peak moments throughout the day. Then you have, let's say, a kind of valley where there's nothing happening, and then there's a peak again. And this is something that you see happening all over the place inside your company. And basically you have these kind of graphs where you see really the peaks, let's say, in the moment that you have the transfers, and it's, let's say, throughout the day. What I told you before, when you looked at the demand modeling, we said that, let's say, one of the drivers for the attractiveness of your itineraries, that's, for example, connection time. And what we see is that, let's say, if the connection time is too high or too low, let's say the connection is not interesting enough for your passenger. So that's something that we need to incorporate when we design our network, because, let's say, if the connection times are not good enough, we lose revenue. So basically, here we have the challenge to optimize, let's say, to build, let's say, the aircraft rotations. So let's say the flights coming in, you need to say, okay, what kind of aircraft will be performed by, and then just see, okay, how does it, let's say, evolve throughout the day. And there you need to look at, okay, how do I optimize the revenue? And the challenge there is that if you look at the medium haul network, it has different characteristics compared to the long haul network. So medium haul network, basically these are, let's say, the Europe flights. So you have, let's say, one aircraft performing several flights in a day. And if you look at your long haul, that's the ICA, the flight goes somewhere to, well, the States and then comes back the day after or the day after. So these are different characteristics. And that's also reflected in the way we do our optimization. So what you see is that our company first tries to optimize the medium haul network. And based on that, it tries to optimize the long haul network. And optimize means trying to, let's say, build the right aircraft rotations. In case it doesn't fit, you re-optimize your medium haul network, and then at some moment you, let's say, come to, let's say, the best solution. That sounds simple, but if you look at, let's say, the optimizing of the medium haul, sorry, I was lagging behind. This is the picture. Apologies. So this is the picture about the expected revenue. So here you see, let's say, the optimal value is 2 hours. So if it's less, let's say, then you are, let's say, missing revenue. And if it's very long, you're also missing revenue. So that's the part that you need to incorporate when you are building, let's say, your medium haul and your long haul networks. Basically what we do when we run the optimization, we try to retime some of the flights, the departure times, the arrival times, just to see whether those connection times are good enough. Based on that, we can compute the expected revenue. And this optimization, if you do it for the medium haul, it takes you on average about 3 hours of computations. So what you try to do is to try to maximize the revenues. So you need to look at the time ranges for those flights. And one specific thing that I also should mention, so one of the things that we don't want, so if you have a business passenger and he's making a transfer, you don't want the business passenger to have a remote boarding. So you want also to have your gates available. And that's quite a severe restriction also when you do your optimization. Basically, if you do your optimization, it takes you 3 hours, say, on average. And there are instances where it takes more than 8 hours to, let's say, do the optimization of your medium haul network. And that means that if you do the iterations between medium haul and long haul, it can take you a very long time. So there the challenge is that we are currently working on is to try to do it in one shot. So we try to build the long haul, medium haul rotations in one shot and see if we can come up with, let's say, good solutions. Check. Everyone still there? Perfect. Yeah. Me too. So I have 2 more challenges. So this challenge is about predictive maintenance. And I think it's always good, if you, let's say, if you are working for an airline, to talk about predictive maintenance because it's about safety of your aircraft. And I think that's the most important thing for any company that flies aircraft. At the beginning of my presentation, I talked about, let's say, this optimal match between commercial wishes and operational capabilities. Commercial wish, of course, is to fly as much as possible. So you don't want your aircraft to be grounded. You want to have, let's say, as much flying as possible. There's a restriction because you need to do maintenance. So how does that compare with each other? Well, here are some key figures. So what you see is that maintenance accounts for about 10 to 15% of your airline cost. Maintenance also accounts for 30% of your ground time usage. And if you talk about operational disruptions, it accounts for 10%. So there's really an urgency to, let's say, do something about this maintenance to really keep things in control. Well, there are different strategies that you have. So the first one is what we call preventive maintenance. So basically you schedule your maintenance in a regular pace and you just, let's say, go into the aircraft and you replace components. Can also mean that sometimes components are replaced too soon because they are not broke yet or they are still functioning quite okay. So there you lose some of the remaining useful life of this component. Can also do corrective maintenance. So if at some moment the component is broke, non-critical, then you need to replace it. So that's just waiting until it's broke and then you do something. That's quite inconvenient for your passengers. So if this happens at an outstation, you need to accommodate your passengers, you need to, let's say, book hotels for them, you also need to, let's say, fly in some of the components just to fix things again. So that makes it quite difficult. So ideally, you would like to use the sensor data of all these components in the aircraft and to see if you could make some kind of prediction of, let's say, the remaining useful life of your components. So these are the different strategies. Just to give you an impression of the first way to, let's say, do this preventive maintenance. So basically, this is a picture where you see the aircraft rotation schedules. So each line is an aircraft rotation, and you see, let's say, a flight from JFK back to Amsterdam to, I forgot then, Denver, and so on. You see 4 of those lines, and this is, let's say, the schedule made by the network department. Then it's given towards, let's say, the engineering and maintenance department, and they need to figure out whether this is okay for them if you talk about maintenance. So what they do is they, let's say, run different scenarios. So one of the scenarios is to say, okay, I just, let's say, have a lot of maintenance slots, but smaller ones. The other option could be to, say, have less slots, but larger ones. And based on these different scenarios, they compute certain KPIs, and based on those KPIs, they can decide whether this is okay or not. And if all scenarios are not okay, then they need to go back to the network department and iterate again. So ideally, you would like to have also an optimization where you create this aircraft rotation schedule together with the maintenance slot. But that's something that's difficult because you need to, let's say, discuss between your network department and between engineering and maintenance. And these are, let's say, 2 different divisions, and that makes it quite challenging business-wise. The other thing that you also could look at, so this is how, let's say, these maintenance slots. So you also need to see, okay, which task will I do in these maintenance slots? So if you have, let's say, good predictive maintenance, you can do it in a smarter way. And so basically, this is what you try to do. Yep. So the idea is what I said before. So you can do, let's say, your corrective maintenance. So when you start with the component is healthy. At some moment it starts deteriorating. At some moment, the health is 0, so it has failed. So there you need to replace things. You don't like to be in this place. So basically what you try to do is you try to use the aircraft data, and let's say at the moment you see that it's deteriorating, you raise an alert. Based on this alert, you try to take some action. That sounds quite simple, but so if you look at your aircraft, so there's aircraft data, and the aircraft data of one aircraft contains 100 million of different data points. So you need to have a good model, trying to understand what's happening inside your data and try to detect those kind of degradation patterns. And that is quite a challenge, and that's, let's say, what we are working on. And you try to use machine learning to optimize, let's say, these alerting thresholds. And basically what you do, so here you see, let's say, the aircraft data of different flights. So here you see aircraft data of 4 components, and you see that it's per second. So it's really, let's say, a lot of different data points. What we try to do is we try to aggregate it to flight level, and here you see for each flight, so it's the departure date time of the flight, you see 4 points representing those 4 components. And basically what you try to see if there's some typical behavior in this. So the idea is that, first you look at this picture where you see this deterioration pattern, and you try to see whether you can also recognize it in this picture. Well, maybe you cannot directly, but if you flip, let's say, the diagram, you see basically this kind of behavior over here, where you see this degradation pattern. So if you have a good machine learning model, it would be able to detect, let's say, the threshold, so which is the period in which the component becomes faulty, and then based on that, the model raises an alert. Based on the alert, the task is created, meaning that a maintenance engineer will go to the plane, will look at the component, and then say, okay, this component is indeed malfunctioning or not. So the point here is, at least to mention that there's always human intervention. So it's not just machine learning taking the action, but it's really, let's say, an engineer, a human, that checks whether the component is really faulty or not. If it's not faulty, it's also information that is needed for the machine learning model again. So also there you have, let's say, the repair feedback. So that's the feedback towards the system, but also input for our machine learning model to improve its learnings. So the challenge here, if you look at degradation patterns, so we are very lucky that we don't have that many degradation patterns in our data. That's also for other airlines. But for your machine learning, it's quite a challenge. So if you would like to, let's say, really learn from the data, you need as much data as possible. So there, basically, you would like to also run your model on the data of other airlines. Well, other airlines are not that willing just to give the data to you. So in some way, you need to do it in a kind of federated way. So there's this approach, it's called federated machine learning, where you try to learn on decentral data, and based on that, try to see if you can, let's say, have good predictions for those thresholds for the alerts. Yep. Last challenge. I'm still, okay, perfect. So you saw a lot of different challenges until now. So I had 5 challenges. And if you look at those challenges, they're sometimes were, let's say, based, let's say, on the mathematics. So sometimes it was not clear which method was the best, or sometimes you need to, let's say, go back to an older method. So there's challenge on the mathematics. There's also challenge on the computational performance. So sometimes, let's say, it takes 3 or 8 hours to, let's say, run your optimization. So that's also something that is not really preferred. And the other part, and I think that's also something that we saw back in these other challenges, is also balancing between different stakeholders. So for this preventive maintenance, there's, let's say, this discussion between network and engineering maintenance. If you look at this QSI expression, this utility function, you see all those kinds of, let's say, different features. These different features are owned by different stakeholders inside your company, meaning that you also need to check with those people, if you, let's say, do training, if they agree on the weights. So it's really kind of business transformation challenge that you need to do to really have people aligned on, say, the things that you would like to do with your organization. Well, on the day of operations, everything comes together. So I think before it was still a bit separated, but on the day of operations, all those challenges come together and you need to do things. So if you have bad weather conditions, or you have technical failures, you need to act immediately. It means that you have to run optimizations, you need to do things, and you need to come up with a solution that's working. Not a good enough, let's say, not a near solution, but the solution should really be working for you. And the way we are doing it, and that's, let's say, the thing I will try to show you in this challenge, that's a challenge that we actually achieved. This is something we are able to do. And basically, what we are using, so in the previous challenge you saw this utility function. Basically what we do here is we have a cost model, we call it cost curves, and basically this is, let's say, the balance between all those different objectives of our business stakeholders. So we discuss with all those stakeholders and we try to say, okay, if you take this decision, or if you try to say, delay a flight like this, what is the impact on your business, on your department, and we try to really have a full overview of what's happening there. And based on that we build what we call cost curves, and that's, let's say, the joint utility function. So what we all say, so cost curves, let's say, is the common currency across all the departments. And it's, let's say, it's used for, let's say, the decision taking in every stage of our planning process. So that is a way also to let's say, ensure that there's consistency in your planning process, let's say from 4 or 5 years until, let's say, 1 day before departure, the day of departure itself. And basically, if you have, let's say, these cost curves computed, this currency, then people can, let's say, look at different GUIs, interfaces, just to check whether it still makes sense for them. So it's really something they can validate, they can look at, and they can really say, these values are okay with me. So they can see what the impact is of delaying a flight or cancelling a flight. That's something that we made available for them. What does it include? Well, everything. So maybe that's a too easy answer, but basically all the hard costs, so things like, for example, passenger report protection costs, so the out-of-pocket expenses, they are included. Also, if you talk about soft cost, so if you take a decision now, it can have impact on future expenses, that's also included. There are also what we call penalties, so artificial penalties, and that's basically the steering that you do in the different applications that are using these cost curves. So sometimes you have kind of business rule to also guide your optimization. These kinds of penalties are also included. This is a picture to explain at least what we do on the day of operations itself. So in the central place is the cost curves. This is what should be included. So this is what we include. This is from the customer journey. So the protection cost, claims, whatever, the fuel, airport, aircraft performance. We also look at the impact on crew, maintenance and cargo. We put things together in this common currency in these cost curves. And based on that we have an application, it's called Sentry. And that's really looking at the day of operations, how to solve the problems that you have. And there it tries to minimize the total expected operational cost. And it also tries to minimize the non-performance cost. To give you an impression, so these cost curves maybe sound a bit abstract, but basically these are visualizations of what, let's say, a flight looks like. So if you talk about cost curves, what we do, let's say, in the preparations for this tool, is that for each flight, We know, let's say, the behavior of all the passengers. We have all the characteristics. So based on this information, we are able to compute the cost curves for this flight, meaning that if you would delay your flight a bit, you have insight in what it would cost you. And the first picture that you see is what we call, let's say, a kind of, let's say, standard mix of passengers. So it's just increasing like this. If you look at the second picture, you see that you have a lot of people, business people, that have very short connection times. So basically here you see that with a short delay, the costs are already much higher. Well, these kind of pictures, we give the names. So this is the standard, the supreme. You have the step change. So here you see that at first there are not that many costs, but at some moment it really increases. And that's because there's a large group of passengers with the same connection. So in that way, you have these kind of cost curves computed for all your flights. And that's what you include when you try to, well, optimize when there are disruptions. So this is the tool that our users are using. So this is used by our operations control center. And this is basically real-time offering you solutions. So if there are disruptions, let's say, it will track those disruptions. It will show, let's say, what's happening in this kind of aircraft rotation schedule again. And then based on that, it will make suggestions whether you should swap flights, delay flights, cancel flights. And this is a very simplified example. I will watch my time. So basically, it's very simplified, but just to give you an impression. So here you see 5 aircraft rotations. You see 3 flights that are being delayed due to weather conditions. So this one, and that one. And you see that there are knock-on effects. So in the end, you see that all 5 aircraft rotations are, let's say, hampered. So in some way you want to find a solution, let's say, where the knock-on effect is minimal. Well, you can try to do it by heart, but in case, let's say, well, you don't manage, Sentry, the tool, comes up with a solution where it swaps 5 flights. And say swapping 5 flights is for humans a bit harder to do than for let's say, the optimization part. But basically what it comes up is with this solution, to swap 5 flights, where you see that in the end, let's say, the 4 first rotations are not impacted anymore, and only on the last aircraft rotation you see that there's still a delay that you need to take. And this is then, let's say, the one with the least impact overall, based on those cost curves. This is the technical picture, for those who are interested. This is all the data that you have. Real challenge to get all the data from all, let's say, the company. You have a preparation step where you pre-process data. You try to come up with predictions about your passengers, about your package, and also about the flight delays. You also try to already do some pre-processing, data processing, because you need to solve an optimization problem. There's a network formulation for the optimization problem that you already try to build. So that's this part. Then the next step is to use the prediction that you made together with the network structure that you created. And based on that, you have your optimization core that's, let's say, running things. So you try to minimize the cost, you try to minimize the crew impact, and the decisions that you can take are, let's say, swapping or canceling and so on. It's the example we just saw before. And basically the results are shown in the tool, for example, like Sentry, but also other tools. This is for the people that are into mathematics. I guess it's you. So basically this is explaining a bit what's behind the optimization problem. So the optimization problem that, let's say, behind is I need to say it correctly, because I'm not that familiar with it, but it's a network-based model formulation. You have nodes, you have edges. The nodes is representing all activities that belong together, so that should be performed, let's say, in one shot. And let's say the edges are connecting different nodes, and in fact are representing in this way kind of flow, and the flow is modeling your aircraft rotation. So notice, let's say, saying, okay, these activities should belong together, and then you try to find, let's say, the right edges to see, okay, how should, let's say, the flow be performed or be built. When you do this just, let's say, in the naive way, it's, let's say, a very large network that you get with almost 6 million edges. Let's say my colleagues did some smart tricks. They call it the idle nodes trick, where they reduced to 370,000 edges. And what you see here, so if you look at, let's say, the median instance, if you run, let's say, the Gurobi solver, and you have your original formulation, it takes you about 46 minutes. And let's say the objective function that you arrive at, so that should be as low as possible, is 4 million something. Let's say the trick with the idle nodes that we do, let's say there the runtime is only 5 minutes. And you see that, let's say, the objective function is a bit more, let's say, than what you achieved over there. And for example, if you compare it with the large neighborhood search, there it also takes 5 minutes, but the objective function, it's not near optimal. The nice thing is if you run it, let's say, on a large instance, so the Roby is not giving you any answer if you use the original MIP. And let's say with this formulation, it's still about 5 minutes. The costs in this case are 40 million, and you can compare it to the large neighborhood search. It's 60 minutes, and it gives you, let's say, 28 million. This is the reason why I want to also share this challenge, because well, for us it was really a big challenge to get this running. So we did some nice things. So it's about mathematics, it's also about, I think, the hardware choice that we make. And here you see that you are really able to solve things, let's say, in real time, if we talk about, let's say, disruptions during the day of operations. This is something, these kind of tools, is something that we did in the partnership. So it's a partnership that we launched, I think, in 2018 together with BCG. So that's the Boston Consultancy Group. And what we do there, and I think that's also nice to mention, is we develop these tools for ourselves, but also in such a way that it can be shared as a service to other airlines. It will then be customized, but it's something that they can also use. That makes it a bit hard for us, because well, the software should be working, and let's say this kind of service that you should deliver. But it's also, let's say, mandatory for yourself to really have, let's say, good software in place. And I think this is then the last slide on Century. I will not go into all the details, but here you see the whole tool suite, so suite of tools let's say we created together with BCG, and they are supporting, let's say, this planning view. So at the beginning we saw a kind of time horizon, let's say, where we have the different steps. What we did is here the same, but let's say we try also to identify the different stakeholders. And let's say when you go, let's say, nearer to the center, you go nearer to the day of operations, and there you see, let's say, all the different, interfaces between different departments, and for each of those phases we create these kind of tools. And I guess this was almost my last slide. This is my last slide. So I would like to thank you for flying with me this morning. If you have any questions, don't hesitate to ask.
Okay, thank you, Jeroen, for very interesting talk. I think we can take 2 questions max because of time.
Go ahead. So I'm only 6 minutes over time, so if you look at what we do in the airline, I'm punctual.
Thank you for an excellent presentation and talk. It feels to me like you're close to optimizing pretty much every aspect of the industry. How far have you removed the human in the decision making? Do you still need managers?
Well, the thing, for example, with cost curves, so that's the part that we incorporate in doing our optimization. These cost curves, from a mathematical point of view, are very simple. It's just a diagram. But if you look at the effort behind, you need to discuss with all your stakeholders. These are tough discussions. You need to convince time and time, again and again, let's say that this is really, let's say, the right cost curve that they're using. So there, let's say, you still have the human involvement. So for me, and I think that was also what I was saying about, for example, QSI. Anytime you have these kind of expressions where you see features, these features are owned by humans. They are owned by departments. So you always need discussions, you always need to have validations. So there you always have the human intervention. And with the tool that you just saw, the Sentry, it's not the tool that takes the decision to do the swaps. In the end, it's the end user in the operation control center to say, okay, this solution is okay for me. And that's also what we saw with predictive maintenance. So if you have, let's say, an alert based on the component, you first look at the component yourself, and you make the judgment as a human whether you should replace it or not.
Hi. With your preventative maintenance scheduling, does it cause you any particular problems if you have components whose failures arrive in like a Poisson process, so you have a memoryless distribution of time to failure, so you can never anticipate a failure, never learn from what's happened already?
So predictive maintenance is quite a challenge, because one of the things, so if you have new aircraft, or let's say there are only new components in there, you know nothing yet. So you rely on the information given by, let's say, the vendor, the provider, and you need to trust him. And at some moment, I think you have specifications saying, okay, this component probably has this remaining useful life. At some moment, after let's say 1 year or 2 years or whatever, you can only then judge whether, let's say, these specifications were correct or not. It's always a very difficult discussion, because based on what can you say, okay, your specifications were not correct. It's very difficult. I was trying to say, so if you, let's say, you have new airline, new components, it's very difficult to see what's happening there. And sometimes if you have totally new things that you did not see before, you also don't know. That's also the reason why you should include this engineer just to check things.
Thank you.